Welcome to sublesson 5.3, Sending Signals to Processes. So a signal is an interrupt request for a process. It's a means to communicate between processes. Signals are sent by various entities on the system. It's, for instance, sent by terminals to take some action. For instance, maybe I'm logging out of my terminal and a signal needs to be sent to kill the current processes running under my user. It can be sent administratively by the system admin. I can tell a process it's time for you to stop, or I'm going to terminate you, or I'm going to interrupt you in some other way. The kernel sends signals for a number of different reasons. It might send a signal to intervene on a process's behalf. If an instance has data waiting for it, it might tell the process you have data waiting, or it might notify it for a different reason. Processes define what are known as handler routines when a signal is sent. This is known as catching a signal. So if the kernel sends a signal to a process, the process needs to plan for that signal. It needs to know this might happen, so it needs to catch that signal. If there's not a handler routine present, the kernel might take some action by default. Programs can also request that most signals, but not all signals, can be blocked or ignored. If it doesn't care about being interrupted, or if it wants to ignore a stop request, it can signal the kernel that it wishes to not do anything. There's a really large number of signals, and many of them are just unused. But here's some of the most important ones here in this table. We'll quickly go through them. The HUP, or the hang-up signal. This means that the controlling terminal has exited, like I logged out of my shell account. The interrupt signal is something like a Control-C. So if there's some process running and you want it to stop, you can say Control-C and that will interrupt it. This is the type of signal that a process might catch and ignore in some cases. You can send signal 9, which is a really mean kind of kill, terminate the process immediately. This signal can't be caught by processes. So if you send a kill -9, that's sending a signal to a process, it will not be able to stop receiving that. There's also a term, which is kind of a nicer version of the kill -9 signal. And there's a segmentation fault, which you'll sometimes see. This almost always indicates some bug or problem in the running process. So let's explore on the command line a little bit. Here I'm logged into my CentOS system. Let's experiment with the term signal first of all. In an earlier lesson, we looked at this Gettysburg Address file when we were learning about VI and Vim. So I can use the Control-Z command to stop that process. Now you can see that it's running. If I type jobs, I can see that that process is stopped in the background of my shell. And we learned before that I could use FG, foreground, at this point to bring that back up to the front. I can also use the pgrep command to search for this process. I can use pgrep -lf, which will search the process tree for the vim command, and I can see that process 2113 is running vim Gettysburg Address, which is exactly what the information I requested. I can kill it at this point. I could type kill 2113. So now it's dead. If I try to bring it back to the foreground with the FG command, you can see it's kind of mad. It says caught deadly signal term finished. So Vim caught the signal and then it quit. Let's view a little more aggressive version of this signal. I will go ahead and Vim the Gettysburg Address again, and I'll use Control-Z to get back to my shell. I'll use pgrep. Notice that I'm using Control-R, the case-insensitive reverse history search. This is a really nice shortcut for me to get back to the pgrep command quickly. I can type enter, and now it's running with process ID 2115. I can type kill -9. This is a shortcut for which signal I want to send from that signal table we saw on the slide. I can use kill -9 on that process ID. Now if I type jobs, it just says killed. And if I type foreground, there's no job running. That process is dead. So notice the difference between just killing the process, where it caught the signal and finished on its own, versus kill -9, where it didn't have a chance to catch the signal. It was just killed administratively by the kernel. So let's look at a hup, which is like a reload command. Syslog is a good example for that. We'll learn more about syslog in a later lesson. For now, it's just good enough to know that syslog is a logging daemon. It's running on the system. I can type pgrep -lf syslog. The rsyslog daemon running with process ID 1104. So I want to see what happens when I send this process a hup signal. So I'm going to look at the system log file, which we'll learn more in detail about later. Just going to tail it and put it in the background so it's just sort of running. This shows me things that are happening on the system. It's the system log. I already know that process ID 1104 is rsyslog, and what I want to do is send it a hang-up signal, a hup. I want it to reboot, reload itself. So I can type sudo kill-hup, and I can give it that process ID 1104. And remember, I have the syslog varlog messages. I'm looking at that in the background. That's what this tail -f is it's running, but it's in the background. So I killed rsyslog, and it logged. It made a log statement, and it says rsyslog was hupped. So basically that means it's reloading itself. Hup is often used to reload configuration. If you edited the configuration of some running daemon, like you changed your syslog configuration, you could send it a hup signal, and it will reload the configuration. So I'll use foreground, and I'll cancel out my tail of the varlog messages. So now it's not running in the background anymore. This was just a few examples of how processes interact with signals.